Hello everyone, in this video we are going to be building a Heston Model Monte Carlo option pricer from scratch in Rust. We are going to be optimizing it for speed using multi-core parallel processing with Rayon. We are also going to be understanding all the mathematical concepts behind the model, including stochastic volatility, correlated Brownian motion, discretization, etc. So before getting into the theory and implementation, let's take a look at the project and what we are going to be building. So in the main.rs file, we have defined all the parameters, and here I have defined all the Heston parameters, the kappa, theta, sigma, etc. and its respective values. We are going to be assuming that all these values are calibrated values, and then here we are going to be defining the option parameters, basically the parameters of the option for which we want to get the expected Heston price for. So this is the underlying assets price, the strike price, and then risk-free interest rate, time to expiry, and whether it's a call or a put. Now to run the simulation, we are going to be using this command, and this command is going to generate 100,000 different paths, and then we are going to be averaging the payoffs of all those different paths, and then we'll get our expected price. And once we run it, see how quickly it ran, and we have the final estimated price to be $10.4. okay, and then it also generates two different images. One is this paths.png. so here the blue line, if you can see, I'll zoom in a bit. So yeah, it represents all the different paths, and then the red line represents the average drifts of all those paths. Okay, and then in the convergence.png, we have the different paths, what price it predicted, and after these many paths, the price converged to approximately $10.4. okay, so yeah, this is what we are going to be building, guys. It's going to be a very exciting build, so stay tuned. Now before jumping into the code directly, let's first understand what Heston model is and how Monte Carlo simulation is used to get the expected options price from the Heston model. So first, let's understand why do we even need the Heston model. So as we know, its predecessor, the Black-Scholes models, considers volatility to be constant, right? But as we can observe in the market, that is never the case. Volatility has a sort of clustering effect that we see in the markets, and as the stock prices drops, the volatility increases. In the options, we can observe that we get a volatility smile skew rather than constant volatility across different options. So to model that, we came up with the Heston model, where we have, instead of one, we have two stochastic differential equations. One models the asset price and other models the volatility itself, that is the variance itself. So these are the two set of stochastic differential equations, and both of them are coupled with each other. So as you can see, the asset price SDE is dependent on the variance stochastic differential equation itself. Now let's understand what each term means. So here the first half represents the drift part, which is the predictable part, and the second part represents the diffusion part, which is the sort of the random part. Okay, so DST is the stock price at time t, and then R is the risk-free interest rate similarly, and dt is the infinitely small time t, and then yeah, this is the variance, and dwt is the Brownian motion value, the random value for this particular equation. And the second one is the mean reverting equation. So basically this equation, intuitively you can think like, as the variance increases, generally the volatility tends to revert back to its long-term mean. So that is what this equation is representing. Again, the first half is the predictable part, the second half is the random part, and here k, which is the kappa value, is the mean reversion speed, theta is the long run variance or the long term volatility that we see, sigma is the volatility of volatility, and and then we have the second Brownian motion shock value dWt. Okay, and the important note is here, important part to think here is that these two Brownian motion values are correlated, they are not independent. Why is that? Because we observe in the markets that as prices falls, the volatility increases. So we can say that these both are negatively correlated. So that we represent using this equation. Now, as you can see in the Heston model, we have these two stochastic differential equations. Now, to solve it, to get the asset price at time t, we cannot simply do it analytically via closed form solutions like we do in the Black-Scholes model, because here you can see that we have these two random processes dependent on each other. So it gets very complex and difficult to arrive at a closed form solution. So instead we solve it via different methods like the fast Fourier method, the Monte Carlo simulation. In this video we are going to discuss about the Monte Carlo way of solving this. So in Monte Carlo simulation, what we do is basically we create thousands and millions of random paths, and if you know, like basically what we do is we follow this property of law of large numbers. So if we sample something enough number of times in a very large amount of time, eventually we get the most expected value of that sample, the average of that sample. We can consider this by an example of, like, if we measure people's height across the world. So if we have enough sample, if we have sampled enough number of people, then we would know what is the average population of the earth. So average height of people on the earth. So that is similar to what we are going to do here. Instead we will generate enough random paths such that we get the most expected value for that particular option. Now there is one more problem, that is we cannot solve these equations computationally in its current form. We need to convert it into a discrete form. And what do I mean by that is, right now it's in a stochastic process continuous form. That is, like, we treat every change as an infinitely small change. But to solve it computationally, we need to define the steps, right? So like from time period t to t plus delta t. So for that reason we need to convert these equations into discrete form, and there is a derivation for that, and that is what I'm going to show you right now. Now to discretize these two stochastic differential equations, we first need to introduce correlation between these two Brownian motions, W1 and W2. As you know that in Heston model, these two Brownian motions have a correlation of rho. So to do that, we use something called as Cholesky decomposition, which basically converts any two random variables, any two independent random variables or independent distributions into correlated variables or distributions, such that they have a covariance structure. And firstly what we do is we define two independent normal distributions, G1 and G2, with mean as 0 and variance as 1, and we assume them to have a covariance structure equal to this matrix. Here the diagonals represent the variance and the non-diagonals represent the covariance or correlation between the two distributions. Okay, and to do the Cholesky decomposition we use this formula. Here this symbol represents the covariance structure, which is this, and L represents the lower triangular matrix, and this is the transpose of that matrix. L is also the Cholesky decomposition factor, which we need to find out, and once we have that, when we multiply it with the particular distribution, we get the correlated distribution between those two independent distributions. Okay, so we first assume L to be equal to this lower triangular matrix and transpose to be equal to this, and once we multiply this, once we do this matrix multiplication, we get this, and this should be equal to this assumed covariance matrix, right? Now we solve the individual cells, so a square should be equal to 1, so we got a is equal to 1, and similarly here, like for this cell, b square plus c square should be equal to 1, so we got c is equal to this, and that's how we got our L to be equal to this particular matrix. And now we finally have our Cholesky decomposition factor, and if we matrix multiply it with those two independent distributions that we assumed in the beginning, z1 and z2, we get the final correlated Brownian motion. So after multiplying, we get w1 to be equal to z1 under root of delta t, and we get w2 to be equal to this particular value here. Also, I forgot to mention, we multiply here by square root of delta t because earlier we were dealing with normal distribution where variance is 1, but in Brownian motion, if Brownian increment is delta t, then the variance must be equal to delta t itself. So to scale the variance as per the Brownian motion, we multiply it by square root of delta t to have a proper variance of delta t. That's why we are multiplying everything by square under root of delta t. Now once we have the correlated Brownian motion equations, we now will discretize the acid price stochastic differential equation. So this particular form is the naive Euler discretization of the acid price SDE, but there is one huge problem here, that is that this particular shock term can rarely become a large negative number. So that can make this entire right hand side a negative value, which basically means that the stock price has now become a negative value, which we obviously know that is not possible in markets. So what we do is, instead of dealing in this space, we deal in log space. So there are two main advantages of dealing in log space. One is that our calculations becomes easier because in log space we can often convert multiplication dynamics into additive dynamics. So that is one case, and the second advantage is that after exponentiating, the values can never be negative. It can be closer to 0, but it can never be less than 0. So for that reason, we convert acid pricing in log space. Now to do calculations in log space, we replace ST with ln ST. And as per stochastic calculus, we know that in the Taylor expansion, the second degree term is non-zero in case of stochastic calculus compared to regular calculus where the second degree term becomes 0. So here, because it's non-zero, we need to include it in calculations while performing the derivation. So once we have that and we assign f is equal to ln s, we derive it once. And the first derivation of ln s is 1 by s, and the second derivation is minus 1 by s square. So we simply substitute these values in our Taylor expansion, and we have this equation. And we can further expand this equation because we know that dst is equal to this particular SDE, right? So the square of this becomes this particular equation. And we know that in Ito multiplication, dt square is 0 because dt is already small, and then after squaring it, it becomes even smaller. So we treat this term as 0, so this part becomes 0, and then dt times dw is also 0, so this term becomes 0, and we only have this particular term where we know that in Ito's lemma dw square is dt. So we have this term left after squaring this. So we simply substitute this value in this series, and we have this particular equation. After that, we simplify it, and then we finally have this equation here. Now as we can see in this equation, that after doing calculation in log space, we have converted the earlier complex SDE into a linear SDE. And you can see that the right hand side is no longer dependent on the ST coefficient, right? And in the next step, what we do is we integrate it over one time step. So we write the ln ST as ln ST plus delta t minus ln ST, and we exponentiate both sides, and after simplifying the exponentiation, we get this final term, which we are going to use in calculations while doing the Monte Carlo simulation. So now we'll discretize the variance stochastic differential equation, and its discretization is going to be much simpler than the discretization of asset price stochastic differential equation that we did previously. So this is the variance SDE formula, and we discretize it using the Euler-Maruyama formula, which represents it like this. And we already have the correlated Brownian motions, so we can get the Brownian motion for the variance using this formula that we had, which will give us a correlated Brownian motion to the asset price Brownian motion. Alright, and then one fix that we need to do here is that in the case when variance is very small and there is a strong random shock, negative random shock, then this can make the variance negative. Alright, and this can become problematic because in the asset price equation we are using under root of variance and here as well. So that will make it imaginary, and that is going to in turn break the simulation. So to prevent that, we use something called as full truncation fix, which is very simple fix where we limit the variance value to 0. So we take a max of variance comma 0, where basically if variance is negative, then by default we will get a value of 0, and if it's positive, then we'll retain its original value. So that will prevent it from becoming negative. And yeah, this we have is the final discretized equation for the variance SDE, and we are going to use this while performing the Monte Carlo simulation. Now let's walk through the code and understand how things are working. So I have divided the code into multiple files. So firstly we have this main.rs file, which is the entry point for the code and from where we trigger the Monte Carlo simulation. And then we have this model.rs file where I have defined this Heston param struct, where we store the Heston calibrated parameter values for like kappa, theta, sigma, rho, and initial variance. And then we have this option.rs file where we store the struct, or where we create the struct for storing the option contract values like the initial stock price, the strike price, the risk-free interest rate and all. And then we have the pricing.rs file. So here is the main logic to calculate the payoff and then to estimate the price from the path that was simulated. And in the simulation.rs file we generate the actual path from the discretized equations that we had derived. Okay, so let's begin with the main.rs file. So firstly we do this to make the Rust analyzer recognize these files, and then we import the respective functions, and then we define the calibrated Heston parameters, and here we have defined the option contract for which we want to get the estimated price for. And then here we define the configuration for our Monte Carlo simulation. So here the n paths tell that we are in total going to generate 100,000 different paths, and then n steps, which is equal to 252, says that each path will have 252 stochastic updates. So that many number of updates must be needed from the discrete formula that we created to generate a path. Okay, so basically it will have 252 number of shocks in each path. Alright, and then we have defined some print statements for better readability. And then what we are doing here is we are creating antithetic pairs. So what we are going to do is we are going to use a variance reduction technique, which is called antithetic, where we divide the number of paths by 2. I'll explain this in detail in a bit when we move to this simulation.rs file. But keep in mind, we are using a Monte Carlo simulation technique to reduce variance and to improve speed, which is called antithetic pairs. All right. And then here, basically, we are starting a timer to check like how fast did we run our simulation. And then we call this price European function with all our Heston parameters, our option parameters in the config, where we'll start running the simulation and calculate the prices. And then the time elapsed, this will tell us how much time it took to run. Okay. And yeah, and once we have the call price, what we do is we now want to verify like how good our system is, or do we have any errors or not. So to verify that, what we do is there is something called as put call parity, which says that if a call and option have same strike and same time to expiry, then they have a relationship between them which is suggested by this formula. So if you have a call and you want to get a put for it, so if you already know the call's price and you want to get the put's price for the same expiry and same strike price, then you can get it via this formula. So similarly, now we have call price, so we try to get the parity put price, the put price according to the parity. Okay, so we use that formula to get that particular put price, and then we run the simulation for that put again. Okay, so this put, if we run the simulation for the same put, we'll get the price according to the Monte Carlo simulation. Okay, and once we have the put price according to the simulation, what we do is we check the difference between the parity put, the price that we got from our parity formula, and then the put price that we got from our simulation formula, and then we check for the difference. If the difference is huge, then it means that there is some error or some issue in our Monte Carlo simulation, and if the difference is near zero, that means that our simulation is close to how it should be. So that's why we do these steps to as a like quality check of how our simulation is. And then in the later part, here we are basically generating the plots that I showed you in the starting of the video, the plot to which shows all the paths that is generated and how the price got converged. Okay, now let's have a deeper look at the actual pricing engine. Now let's take a look at this price European function using which we price the European options. So it accepts the Heston parameters, the option parameters, the configuration parameters of Monte Carlo, and then the seed. So the seed is basically a random number provided by the user, which is helpful in generating the random paths later on. So basically, along with generating those random numbers, it is also helpful in reproducibility. So this is like an identity for each of those paths. So we call it the master seed, and then here we have defined the discount factor. So what happens is when we simulate path, we get the price for an option at the time of expiry, but we want the current price, right? So what do we do, as we are working in a risk neutral framework? So we simply discount the price at the time of expiry to get the current price. Okay, so we discount it by the risk free interest rate. So this is the value for that. And then we have the total number of paths. So initially we had defined the total number of paths as 100,000, right? So we divided it by 2, which becomes 50,000. And this is for the same reason I told earlier, for variance, for a technique called antithesis, which is a variance reduction technique. So this is basically helpful in two ways. One, now Monte Carlo, we have to simulate half the number of paths, so it reduces the time, it increases the efficiency. But the major reason is that what we do in antithesis is, let's say the simulation from those discrete formulas have generated a path. So in antithesis, what we do is we generate a mirror of that path. Okay, we have a path and then we simply replicate a path, a mirror of that path, the complete opposite. So what it does is, let's say that particular path which was generated gives a inflated price or overpriced option. Then the simple mirror image of that path will give the price to be as underpriced. So what will happen is that if there is any noise in both of them, then they'll average out and cancel each other. So that is why we call it variance reduction. And remember, like, all those paths are random. So averaging all those negatively correlated random paths simply give us the best average by cancelling out the noise. Alright, and then we move on to our loop. Okay, so here basically we want the sum of the payoff and the payoff square sum, and we'll run this loop from 0 to 50,000. Half is 50,000. Okay, and then we call this into parator. Basically this function is from Rayon library, which will run the loop in multiple threads, and each thread can utilize different cores of the CPU, so that will make the simulation much faster. And we can do that because, like, in Monte Carlo simulation, each path is independent, right? No two paths are dependent on each other, so we can easily use multi-core threading here. And then for each index, for each path we initialize a RNG. So basically this will initialize a random number generator which will use the seed that was provided by the user, and then simply multiply it by this big constant. So this will again provide this multiplication factor some randomness to the seed, so that it's not very predictive, right? Because, like, if this I we know is iterative, so it will be 0, 1, 2, 3, so that will become very predictive. So instead we multiply with this huge number to make the random numbers a bit more random and unpredictable. So once we have the initialized RNG, we then call this simulate path antithetic function, where we generate the actual path using the Heston parameters, the option, config, and the RNG that we just initialized. Okay, we'll have a look at this path in a minute, path generation function in a minute. So what this will do is, this will finally return S1 and S2. S1 and S2 are basically the price at the time of expiry for both the paths. So S1 is the price of that option for that path at the time of expiry, and S2 is the price of the option for the anti of that path, the mirror image of that path. So we get both of these prices, and then we have this payoff function defined here, where we basically calculate the payoff. So we all know the formula of for a call option payoff is the current price minus the strike price, and for the put it is the strike price minus the current price. Okay, so we call this payoff function with the first path that we create, and then the antithetic of that path. Okay, and then once we have the payoff, we simply average the payoff, and then we have our average payoff, and we return it. And then what this reduce function will do is, as we get the results of all those iterations of all those paths, it will store it, and it will sum all those paths. Okay, so then we'll have basically the sum of all the average payoffs, and then here we get the mean payoff. So we divide the payoff sum by the number of paths that we generated. So now we have the actual average mean payoff, and then we calculate the variance using the probability theory variance formula and the standard error, and then price, as I told you. Now that we have the mean payoff, we can simply discount it and then we'll get the current price. So that is how the current price is generated, and this is the price that we got when I ran the Monte Carlo simulation at the beginning of this tutorial. Now let's have a look at this simulate path antithetic function, where we are generating those simulation paths. Now in this function we are simulating a path and its antithetic, that is its mirror image, and this function accepts all these parameters, and in this line we are dividing the time to expiry of that option with the number of steps needed to simulate that path, so that upon dividing we get the size of each step, size of each jump, so that we represent by dt, and then here we will take under root of dt. This will be helpful because we know that the Brownian motion scales by under root of dt on every dt increment, and then here we are doing some Cholesky pre-composition, pre-calculation. This will be used to generate the correlated Brownian motion equations later, and then we are extracting the underlying asset price and then initial variance, and it is going to be remain the same for its antithetic as well. And then here we are going to run a for loop for all the steps needed to simulate a path. So there are 252 steps, so for each step will iterate over this, and then on every iteration we'll generate a standard normal distribution, two standard normal distributions z1 z2, and using those distributions and the Cholesky decomposition that we discussed about in the theory part, we will generate correlated Brownian motion equation. So dw1 will be z1 times under root of dt, and dw2 will be basically this Cholesky factor, this pre-calculation that we did, and then multiplied by the square root of dt. Alright, and here we are basically applying the full truncation scheme to make sure that the variance remains positive. Here we are taking the square root of the variance, and then this basically is the Log-Euler discretization, which we get after discretizing the asset price stochastic differential equation of the Heston model, and this is the Euler-Maruyama discretization, which we get after discretizing the variance stochastic differential equation of the Heston model. Okay, and similarly for the antithetic, everything remains the same. We just negate or add a negative sign for the standard normal distributions that we generated initially, and it will generate a mirror imaged path. Okay, and once we run it for every step, at the end after the loop is finished, we'll have the path and its antithetic path's final price at the time of expiry. So this we will return, and we are going to generate payoff as we discussed. From it we'll calculate the average payoff divided by the number of paths, and we'll finally have the final estimated price. So that is it guys for this tutorial. I hope you find this helpful. If you have any doubts, any questions, let me know in the comments down below. Thank you so much for watching.